Alright, next up, as promised, we have logarithms, and the goal in this section is to become good at differentiating functions involving logs. So, let's see, let's suppose f of x is equal to log to the base a of x. Right, so my function is this basic log function, and the question is, what's the derivative? What is f prime of x? In the last section, I just straight up told you how to differentiate a to the x, right? I just gave you the derivative. That's because deriving it takes some time. But here, once we know how to differentiate exponential functions, we can actually differentiate this function log to the base a fairly easily. So let's manipulate this a little bit. What does this mean? This means that a to the f of x should equal x. Right, that's the definition of logs. That's what logs mean. If f of x is log to the base a of x, that means a raised to this number. F of x is x. How about I go ahead and I differentiate both sides? Right, these functions are equal, so their derivatives should be equal. All right, so we'll differentiate both sides of the equation. And as we just saw, we now know how to differentiate functions like a to the f of x, right? This is, the derivative would be a to the f of x times the derivative of the exponent, f prime of x. And I'm forgetting something, I need to make a little bit more space here, times the natural log of a, right? If it was e, it wouldn't be there because that's just 1, but since this is an arbitrary base, this would be times ln of a. So there's the derivative of the left-hand side. Derivative of the right-hand side is just 1. Well, that means I can actually solve now for f prime of x, which is what I wanted, right? I want to know the derivative of f. If I just solve for f prime of x, that means the derivative is 1 over natural log of a times a to the f of x. And this is all true, but this is sort of an ugly form right now. A to the f of x, well, that's my original function. What is a to the f of x? Come back to this line. A to the f of x, that just equals x, right? So my derivative is 1 over ln of a times a, times a to the f of x, which is just x. Awesome, so there's the derivative. We found it. If f of x is log to the base a of x, the derivative, f prime of x, is 1 over ln of a times x. So I'll write this concisely. And I'll write this concisely. The derivative of log to the base a of x is 1 over ln of a times x. Well, just like with exponential functions, we don't often work with base a, right? The most common base we'll use with logs is e, the natural log. So that means that the derivative of ln of x is 1 over ln of e. But ln of e is just 1, so this is just 1 over x. So you commit these to memory, right? These are the derivatives of the log functions. This one will be the one we use most often. Derivative of natural log of x is 1 over x. But still, sometimes you'll have other bases, so you'll have to remember, for other bases, it's not just 1 over x. It's got this extra ln of a factor in the denominator. So a couple of simple examples. Let's say f of x is log to the base 6 of x. What's my derivative? Well, here we have log to the base a, but a is 6. So the derivative is just going to be 1 over ln of 6 times x. Let's see, example B, we'll do These are both interesting. How about we do ln f of x is ln of x squared. So full disclosure, as this is written right now, this is a composition, right? Instead of having ln of x, I've taken ln of x and I've thrown into it, I've replaced it, I've plugged into it this x squared function. Right, so I have a composition of functions here, meaning as it stands, the way you would differentiate that is using the chain rule for natural logs. But I haven't told you how to do that yet. There is another way. The other way is to use your log rules first. And this is really commonplace. Anytime you're differentiating log functions, it's usually a good idea to simplify them using your log properties first, because simplifying before you differentiate makes the differentiation a lot easier. So what can I do here? Well, I got x squared on the inside. Remember, powers can come outside as constant multiples, right? So this is 2 times ln of x. Those are algebraically equivalent functions, just by the properties of logarithms. And that makes differentiating a whole lot easier. The derivative now is going to be 2 times the derivative of ln of x, which, according to that formula over there, is just 1 over x. And I would never really write it like that. I would write it as 2 over x. So remember this, because this is something that pops up all the time. Anytime you differentiate, before you differentiate, it makes your life a lot easier to simplify before you differentiate, if you can, right? Rather than simplifying after you differentiate, because usually differentiating makes things more complicated. And one really, really common simplification you can do is, when you're working with log functions, look for log properties that you can use. And so always try to simplify before you differentiate if you can. We'll do one more, c. Let's go f of x is x cubed times ln of x. Actually, we do product rule too often. Let's go with a quotient. Let's go ln of x over x cubed. Okay, so I look at this, I have a quotient, so if I want to find the derivative, I use the quotient rule. Right, quotient rule says, okay, my derivative is going to be low d high, bottom, times the derivative of the top. Let's just do this in situ right now. Derivative of ln of x is 1 over x, right, by our formula we just had, minus the top times the derivative of the bottom, so minus ln of x times derivative of the bottom, 3x squared, all over the bottom squared, x cubed squared. And we're done differentiating, but I think we can clean this up a little bit. What do we have? This x down here cancels with one of those and leaves me with x squared. I've got x squared common to both of these expressions. Let's factor it out. X squared times, if I pull it out from here, I'm just left with 1. And over here, I'm left with minus 3 times ln of x. Again, notice the order here. When you write functions, you tend to sort of order them in increasing complexity. That's why I wrote the 3 out front. It looks better. All over x cubed squared, multiply these exponents together, that's x to the 6. And there's one more simplification I can do. Cancel out an x squared with 2 of these guys and make that x to the 4th. So there's our derivative. But that said, the next question is, just like the last section, the next question is, what if I have compositions, right? What if I didn't simplify this? Can I still differentiate ln of x squared? And the answer is yes, we just need to apply the chain rule. So I'll show you how to do that now. Alright, so chain rule. We'll just go through the special case for log functions. What you typically have is something like this. Log to the base a of, instead of x, it's some function of x. Alright, so what's the derivative? Well, chain rule says, okay, differentiate the outside first, and leave the inside the same. So on the outside I've got log to the base a of f of x. So how do you differentiate logs? Well, it's 1 over ln of a times, it was x before because x was our inside function, but now it's f of x, so times f of x. So that's the derivative of the outside function evaluated at the inside, but then times the derivative of the inside. So times the derivative of f times f prime of x. And I suppose I'll leave it in this form. Alright, so there's the chain rule being applied to compositions of these log functions. And this is, last but not least, this is our special case of the chain rule. Special case number 3. It's also, I think, the last special case of the chain rule. So if you know these 3 cases we've gone through, then that will suffice. But I'll point out that again, the even more special case of this is when you don't have arbitrary base, you've got natural log. And it just looks a whole lot better. If we take the derivative of ln of a function of x, what do I have? I've got 1 over ln of e, so just 1 over f of x times f prime of x. And people often just write this as f prime of x over f of x. Alright, so again, it's a formula you need to commit to memory, but it's not a hard formula to use, or even really to memorize. Alright, it says if you want to differentiate ln of a function of x, you put the function in the denominator, and you put the derivative of that function in the numerator. So just like the last section, what we need to do is several examples to illustrate how this works. So for example, A, let's say y is ln of 6x. Well, what do I have? I've got natural log of a function of x, right? So my derivative, dy dx, or y prime, is, remember how this works, right? It's 1 over the inside function, so 1 over 6x times the derivative of the inside function, 6x. So what's that? We've got 1 over 6x times the derivative of 6x, which is just times 6. And actually what happens here, well, these 6's cancel, right? So I have 1 over x. And there's the derivative. Kind of interesting, right? Derivative of ln of x is 1 over x. Well, so is derivative of ln of 6x. That can happen, right? Different functions can have the same derivative. I've also broken my rule here. I've sort of told you, if you can simplify before you differentiate, do so. Right? And I have log rules that actually tell me that y is, if it's ln of 6x, what is log of a product? Log of a product is a sum of logs. Right? So I can write this as ln of 6 plus ln of x. So now if I differentiate, I don't actually have to use the chain rule at all. I just have to differentiate each function individually. What's the derivative of ln of 6? Think about this for a moment. It's just a number, right? ln of 6, plug it into your calculator, it's some number. Can't think off the top of my head what it would be. Something a little bit bigger than 2, I think. But derivative of a constant is 0, right? So that's 0 plus derivative of ln of x, 1 over x. So, same answer either way, and we should get the same answer either way as long as the math is correct. So you can do this as well. And as I said, if you can simplify before, do it. And it makes your life a lot easier. Alright, here's B. Let's say f of x is ln of 2 plus x cubed. Well, if you want to simplify here, you might be tempted to, but there is no simplification I can do, right? Logs of products and logs of quotients, I can break them up, but logs of sums and differences, there's no rules here, right? I cannot break this up. There's no simplification I can do. But that's okay, because differentiating it shouldn't be too bad. It is log of a function of x, so our derivative is going to be 1 over that function, 2 plus x cubed, times, and let's just do this one in situ, times the derivative of that function. Derivative of 2 plus x cubed is 0 plus 3x squared. And I always sort of write it after because I have to think about what it is, but when I'm finished, I would usually just write it as a single quotient. 3x squared over 2 plus x cubed. Alright, so we'll wrap up the difficulty a little bit. Here's our function e to the x squared times ln of x. So how do we differentiate it? Well, it's not just log of a function of x, it's not just ln of x. It is first and foremost, it's a product. Right? It's a product of two functions, so to differentiate, we use the product rule. So the product rule says it's going to be the first function, e to the x squared, times the derivative of the second, ln of x, plus the derivative of the first function, derivative of e to the x squared, times the second function, ln of x. Haven't differentiated anything, just use the form of the product rule to break this derivative into simpler pieces. And each of these pieces I think are pretty easy. Derivative of ln of x, as long as you've committed to memory by now, that's just 1 over x. And plus this one, well, here's special case number 2 of the chain rule. I've got e to a function of x, so the derivative is going to be e to that same function, e to the x squared, times the derivative of the exponent. Derivative of x squared is times 2x. And then finally, times natural log of x. So I can clean this up and make this look prettier. And also I'm tempted, since I've got e to the x squared common both of them, let's factor that out. So e to the x squared times 1 over x plus 2x ln of x. There's our derivative. Alright, try this one. Try this one on your own. Just pause the video, take a moment to try this one. It's g of x is 3x to the 4th plus x over natural log of x. And then when you've unpaused it, I will just go through this. What do we have? Well, it's a quotient, right? First and foremost, it's a quotient of functions, so the derivative should be computed using the quotient rule. It's going to be low d high, bottom, times the derivative of the top, and these derivatives aren't bad, so let's just compute them on the fly. Derivative of the top is going to be 3 times 4 is 12, x cubed, plus derivative of x is plus 1, minus the top, 3x to the 4th plus x, times the derivative of the bottom, derivative of natural log of x. Using our formula, it's 1 over x. Not really using a formula, I should say. It's just, you commit this to memory now. You know forevermore, derivative of natural log of x is 1 over x. This is a terrible straight line, but over the bottom squared. ln of x squared. Brackets here are really important, by the way. ln of x all squared is not the same as ln of x squared. That would be read as a natural log of the function x squared, which is very different. So be careful with that one. And I suppose there's some minor simplification I can do. So let's write this out front, it'll look prettier. 12x cubed plus 1 times ln of x minus, let's divide each of these terms by x. Right, so this will be minus 3x cubed minus 1. Distributing that negative to both terms over ln of x squared. Let's see, what else do we have? I've only got 2 or 3 more examples I want to do. I think we're on E. Let's do y is log of square root of 3x plus 1. So first thing I'll remind you is if there's no base written, it's usually understood to mean base 10. So log to the base 10, or sorry, log base 10 of square root of 3x plus 1. And first thing I'll do is remember when we differentiate, we don't like square roots, we like powers. So I'll write that as power to the 1/2. And we'll differentiate it. So dy over dx is 1 over the inside function, right? 1 over the inside function, 3x plus 1 to the 1/2. But remember, this isn't natural log. This is log to the base, log base 10. So I need ln of 10 out front there in the denominator. Right, that's the unfortunate fact that we're not working with base e. It adds this extra term here. And then times the derivative of the inside function. Derivative of 3x plus 1 to the 1/2. So that's what? That's 1 over log base 10 of 3x plus 1 to the 1/2 times, okay, I've got a function to a power, so we're going to use special case of the chain rule number 1 here. It's going to be 1/2 comes out front, inside stays the same, 3x plus 1, and then we lower the power by 1, minus 1/2. Times the derivative of the inside of this. So derivative of 3x plus 1 is times 3. And there's more simplification we can do, right? There's the derivative, but this can be cleaned up quite a lot. I've got a 3 on top, so 3 on top. Everything else is actually down on the bottom here, right? 1/2 puts the 2 down on the bottom, so 2 times natural log of 10. And if I write this negative exponent down on the bottom, I've got square root of 3x plus 1 times square root of 3x plus 1 is times just 3x plus 1. Right? Add the exponents together. 1/2 plus 1/2 is 1. And there's our derivative. However, I did this in kind of a silly way because I didn't simplify it before I differentiated, which means afterwards the simplification down to here is a whole lot harder. I have to do a whole lot more algebra to get to this final answer. Right? If I had gone one step further, write this power out front, 1/2 times log of 3x plus 1, now it's a whole lot easier to differentiate. Right? Now it's just dy dx is 1/2 times, okay, derivative of log to the base 10 of 3x plus 1 is 1 over ln of 10 times the inside function, 3x plus 1, times the derivative of the inside. Derivative of the inside is 3. And now we have exactly the same answer as we just had, right? 3 up top, everything else down below. 2 times ln of 10 times 3x plus 1. So same answer, but a lot easier to get there. So anytime you're working with logs, when you're differentiating logs, simplify them first if you can. Let's see, F. So I'm just going through lots of problems here. It's the best way to learn this stuff is to work through lots of problems, right? And it's even better if you're working lots on your own, but I suppose that's what homework for. That's what homework is for. So we'll keep working through some problems. I've only got a few more. But in truth, the reason I'm so good at this stuff is not because I'm naturally really good at math. It's because I've differentiated probably tens and the tens of thousands of functions, right? Repetition is really how you build up getting good at this stuff. So do it over and over and over again, and it will become an easier and more natural process, I promise. Let's see. F of x is log to the base 2 of x plus 5 all to the power of 6. So this is quite a complicated function, right? There's a lot of compositions happening here. We've taken x plus 5 and we've plugged that into this log base 2 function, and then we've taken log base 2 function, we've plugged that into something that raises everything to the power 6. So we've got these three compositions going on, and we'll work through this, right? We'll work through this step by step. And we'll work sort of from the outside in. So what do I have on the outside? Well, it's this function all raised to the power 6, right? So I've got a function raised to the power 6. So this is our special case of the chain rule number 1. Function raised to the 6 is going to be, the derivative will be 6 out front. The inside stays the same. Power lowers by 1. And then what? Times the derivative of the inside. Derivative of log base 2 of x plus 5. Okay, so we've converted this harder derivative of this whole thing down to a simpler derivative. Now we need to work that guy out. So this is 6 times log base 2 x plus 5 to the power of 5. Now what? Well, I've got log base 2 of a function, so my derivative should be 1 over ln of 2 times the inside function, x plus 5, times the derivative of the inside function, x plus 5. So now I need to work out that derivative, right? We've gone from differentiating this whole thing, which is tricky, to a simpler derivative, and now the only derivative I need to find now is this very simple thing, derivative of x plus 5. So finally, we've got 6 log base 2 x plus 5 all to the power 5 times 1 over ln of 2 times x plus 5 times the derivative of x plus 5 is just times 1. And if you've wondered why it's called the chain rule, this is why. Because we've got this chain of compositions, and I can make this chain as long as I want. I could compose function with function with function over and over and over again, and the derivative using the chain rule is just going through this chain of compositions, right? Differentiate the outside times the derivative of the inside, and then the derivative of the inside here, we found that derivative, which involves the derivative of the inside of this thing, and so on. Right, but it's this mechanical process, right? It's just working from the outside in and going through and finding derivative after derivative as necessary. Alright, here's the last one I have written down, and I guess the last one we'll do. It is the square root of the natural log of 2 minus, let's go, x times e to the x squared. Actually not what I've written down at all, which really mixes this up. But try this. If you can differentiate this, I think you have a really good handle on differentiation. And you should get to the point where you can differentiate a function like this, no problem, because it involves, I think, pretty much all the rules. There's no quotient rule here, but it still is mechanically going through and using rule after rule in the appropriate spot. So try this one, and see if we get to the same spot. First thing I'll do, again, we don't work with square roots when we differentiate, so there's ln of 2 minus x e to the x squared to the 1/2. So my derivative, I've got a function raised to the 1/2, so this would be 1/2 times ln of 2 minus x e to the x squared, the minus 1/2, right? Inside stays the same, lower the power by 1, times the derivative of the inside. ln of 2 minus x e to the x squared. No simplification I can do there, logs of differences, there's nothing I can do, so we're just going to have to differentiate that. This first piece, I'm going to go straight back to square roots because there's where we started. So this is 1 over 2 times the square root of that original function. Okay. Times what? Times this derivative. So times derivative of ln of a function is 1 over that function. 1 over that function, ln of 2 minus x e to the x squared, times the derivative of the inside, times the derivative of the inside. Derivative of 2 minus x e to the x squared. Alright, so now we need to differentiate that. So that's going to be 1 over 2 square root of stuff alright, square root of stuff times 1 over, I keep turn this into a single fraction, 1 over a whole bunch of stuff, I just didn't realize it on this line. Ln of 2 minus x e to the x squared. Oh, what I can actually do is I've got a 1/2 power and a whole power, so I can write that as ln of 2 minus x e to the x squared to the power of 3/2, but we'll do that on the next line. Times this derivative. Derivative of 2 is 0, minus this stuff. So minus derivative of x e to the x squared. And this is now a product rule, right? I've got a product of functions. Let's just differentiate this in situ. Let's finish this on this line, so I won't write out what the product rule form is. We'll just write down the whole derivative. It's the first function, x, times the derivative of the second. So I've got e to a function of x. So the derivative of the second is going to be e to that function of x times the derivative of the exponent. Derivative of x squared is times 2x, plus the derivative of the first function is just 1, times the second function, e to the x squared. Close bracket. Alright. And I think with that we can clean up this whole thing. How are we going to write the top? Let's write the top as, let's factor out e to the x squared. E to the x squared times, what do I have? well, I have a minus, so let's actually put the minus out front too. Minus e to the x squared times, what am I left with? I'm left with 2x squared plus 1 all over everything that was down at the bottom, and I suggested how we can clean this up. This is 2 times, this is a 1/2 power, this is a power of 1, so that's just going to be ln of 2 minus x e to the x squared to the 3/2. There's the derivative. Again, up here we've already found the derivative. I've just cleaned it up a little bit on this line. So, in this class we will be differentiating again and again and again. This is sort of the end of all of our differentiation techniques we'll use. But because all of our applications, everything we use derivatives for, basically the first step of any question will be to find the derivative of some function. Because of that, it's really important that you're good at differentiating. To be honest, none of the applications we work with will probably ever have a function as complicated as the one we just went through. But still, to convince yourself and really prove that you can differentiate, that you're good at differentiating, you should be able to go through and do a derivative like this one. Because it's this mechanical process, and as long as you understand the rules and the steps and just how to play the game, you can at this point differentiate really any function that anyone gives you, no matter how complicated it is. Yeah, thanks.